Okay, so I'm going to talk about infinite limits. And this is basically extension to regular limits, but this is like a special case where the graph just goes on infinitely and it never actually hits the limit. So we can't really pinpoint exactly what the number is in the middle just because it just doesn't work like that. So I'll give an example. So we have 3 over x minus 2. And we're going to say the limit as x approaches 2. So what happens is in this graph, if I graph it out, at x is 2, the graph does something like this. And it never actually hits 2. And it goes infinitely down negative and infinitely up positive at 2. So if we split it up into x goes to 2 on the left side, we're going to see that 3 over, and we're going to put like a we're going to put a 2 on the left side. So I'm just going to say 1.99999 minus 2. And this is actually about, just because on the left side, if you're going to do a left side, you have to pick something that's really, really close to 2, but not 2. So 1.999 is to the left of 2 and really close to it. And you get about negative 3,000. So that means that when the x is 1.999, the y is at negative 3,000, all the way down there. That's where the y is. And x is at 1.999. Now if we look at to the right, we're going to put 3 over 2.001 because that's really close to 2 minus 2, and that's about 3,000. So that means on this side it's all the way up here, 3,000. So obviously you can't use our technique we used before where we're like, okay, well it's about this much, just because the difference is so ridiculously high. So this is what you call an infinite limit, where there's not really a limit at all. It just, one side goes positive and the other side goes negative. It just goes to infinity. So we're going to talk about how to find infinite limits, and we're going to figure out we're going to figure out how can we classify it as an infinite limit before we even really look at it. So let's see. We're going to determine the limits just by looking at the graph. So if we look at a graph like this, we can try to figure out what this graph actually, how would you pretty much get, like, what would be the equation of this graph? So when you look at infinite limits, normally a graph goes on infinitely if it's divided by 0 and it has a number on the top that's not 0. So I'm just going to say n, where n does not equal 0. And this is an infinite limit. Infinite limit. And you have to watch out for these because it's kind of hard to really say, oh well, it's going to be this or it's going to be this, just because you have to watch out if it goes on infinitely. So you can't really just check the left side and make a prediction based off the left side, or you just can't check the right side and make a prediction off the right side. So when you look at this, following this definition, if the asymptote, this is called the asymptote, where it doesn't touch. If the asymptote is at x equals 1, that means on the denominator it has to go to 0. So I could just say x minus 1. And at the top it doesn't really matter. Just because we see a 1 right here, I'm going to say that the top should be negative 1. And the reason because if the y-intercept is at 1, if we do y equals negative 1 over x minus 1, when x is 0, we get negative 1 over negative 1, which is equal to 1. So you want to try and find a y that fulfills this x y-intercept, and then make sure that the denominator goes to 0. And you cannot have this 0. Because if it's 0, then it's not an infinite limit. It's a standard limit. So this is what you call a vertical asymptote going up and down. And there could be multiple vertical asymptotes. And I'll give a quick example of that using a trig function. And we're going to do f of x is equal to cotangent x. And if you don't even know like what the graph of cotangent is, this infinite limit would actually help you derive it. It'll help you figure out what it is, the graph of cotangent x. So we know we have to try and get this bottom to be 0. And how would we do that? Well, cotangent is 1 over tangent. And we know tangent is equal to sine over cosine. So 1 over tangent is going to be the reciprocal of this, which is cotangent, which is going to be cosine x over sine x. Okay, so if we want the bottom to be 0, we have to figure out when is sine x 0. And if we look at the sine graph, we see that sine is 0 at pi over 2, pi, 2 pi, 3 pi. And this is when sine is 0, and cosine is not 0 at that. It's actually 1, negative 1, and such. So what happens is that when we're at 0 on this graph, when we're at 0, sine is at 0, so it's divided, so it's in infinity, and cosine is at 1, so it's going to be positive. So it's going to look like this, where there's an asymptote right at the axis. So it's going to look like it's heading up, and then swing down like that. And right here is going to be the next asymptote at pi, because that's the next time sine is 0. And this is going to be a negative, so this graph looks good, just because it goes positive cosine, because cosine's 1, and then down here, cosine is negative 1. So it's going to be negative infinity. So 1 over 0 is infinity. Negative 1 over 0 is equal to negative infinity, which kind of makes sense. So if we follow the same pattern, it will just look like this. And it's going to be those are all asymptotes, and these asymptotes, this is 2 pi, this is 3 pi, this is negative 2 pi, this is negative pi, sorry about that. And it's going to keep going, and we created this graph just by listing out the asymptotes of this. And you can do this for any graph you want, as long as you figure out the asymptotes. If the bottom is 0 and the top is positive, it goes to infinity. This is one of the special things about limits, is that you could pretty much create your own you could pretty much create your own graphs, or you could check graphs a lot easier just by checking the limits. Alright, this is gonna be this is gonna be it for the limits for now. And I think next time I might be going into actually creating a derivative and the tangent lines.